Dr. Jurgen. It's a pleasure and privilege to be the first to speak as part of the inauguration of this project. Um, I will just mention a couple of things about my relationship with the IIT Roorkee as well. So the Himalayas, of course, brings us together. This is the Shingba Rhododendron Sanctuary in Sikkim, where we have one of our field sites. Um, so I started most of my eco-hydrology work in the Western Ghats. So I have two basins in the Western Ghats. And for a long time, this has been sustained through collaboration between the UK and India. And we have had a series of visitors, eminent hydrologists, Professor Keith Bevan and Professor Sampurna Bronzil, Mark Mulligan, Nick Chappell from the UK. And I hope that as part of this project, we will have German visitors to both my catchments in the Western Ghats as well as in the Himalayas. So I look forward to that. So from the Western Ghats, I moved to the Himalayas, mainly because of getting a project which was based in Sikkim in Northeast India, a very biodiverse hotspot. So this is just to show that I have these two instrumented long-term catchments in the Western Ghats, and then I moved to Sikkim, where we have instrumented catchments, and then we moved to Uttarakhand as well. And the two people who have played a very important role in the work that I have been doing with them and sustained by their interest as well and their commitment to field hydrology. Dr. Sumit Sen, who is a faculty at IIT Roorkee, many of you would be knowing, and then Manish Kumar, who's my PhD student who is about to graduate. And so both of whom have been very active in my collaboration over the years, and I've had the pleasure and privilege of visiting IIT Roorkee as well. So this is basically a little bit of a context and connection. So I'll just the talk is going to be a little bit of overall context. Then I'll focus more on eco-hydrology, both local and regional issues. Some emerging concerns. I will also try to assess some of the knowledge gaps and how we can move forward. So, of course, climate change is only one aspect of global change, and there are land use and land cover change is the biggest driver of global change, and that is this case for the Himalayas as well. And we have humans have transformed carbon, nitrogen, and water cycles. There are invasive species coming in, which is also part of global change. And apart from climate change, you have a CO2 fertilization effect, and you have hydrologic responses. So climate change and climate variability and hazards in the Himalayas should be seen in the context of all these different aspects of global change. So just to bring some of the background information especially for our German friends and colleagues, since the early 1950s, there has been a low to moderate decline in the Indian monsoon. And this has not been captured very well by our climate models. So they have not been able to simulate this decline in the Indian monsoon. My colleagues and friends in the Indian Institute of Tropical Meteorology who have been researching the reasons for this decline in the Indian monsoon attributed to the decline in the thermal gradient between the warming seas and the Indian landmass, which is a big driver of the monsoon. So anyway, there are other climate scientists who have other views on the reasons for the decline. But a lot of our very smart climate scientists are hard at work to ensure that our climate models are going to improve. And so if they are able to simulate these observed declines in the Indian monsoon, then we know that their ability to predict the future will be better. So apart from the low to moderate decline in the overall rainfall, the other aspect that has changed is that the amount of rainfall that is coming in different rainfall intensity regimes has changed. So we see a shift. You can see that the rain which is exceeding 150 millimeters or more in a day, those events have been increasing. Similarly, for 200 millimeters in a single day, and so on. And you can see that the low and moderate events are declining, and the importance of the more intense rain events is increasing. So you can imagine you have a low to moderate decline in the overall monsoon, and yet you have a shift towards more frequent and intense rain events. So that is basically one of the, it's a very quick summary, and so I was part of a team which investigated the influence of ENSO and Indian Ocean Dipole and many other teleconnections that have an impact on the very complex Indian monsoon. This is an active area of research. I'm not a monsoon scientist, but I did do a little bit of it to understand the context. And if you see the decline, which is not captured by most of the climate models, you can see that part of the Western Himalayas are showing up, part of the Eastern Himalayas are showing up. Western Ghats has particularly been impacted a lot by this decline, and we have seen that even in our hydrologic data and so on. So that's just the context. And however, just to point out that many climate models predict a much more wetter climate in many parts of India in the future. So it's very likely that this decline that we are seeing may get reversed eventually. And also, I hope that our climate models will also improve in giving us more confidence. And of course, warming. Now, that's the one part of what climate change that is completely consistent with our observations. And in fact, the rate of warming in the Himalayas is generally greater than the global average. And so it's a very vulnerable region to climate change. So in terms of start of summer and end of summer and spring, these are all phenological trends that are already being observed in the Himalayas in terms of vegetation response. There are other things that I don't work on, but we know that the Himalayas are being impacted by that. So for example, nitrogen deposition rates are pretty high. So that's another big driver of changes in terms of vegetation response. It's also potentially a hazard depending on the ecosystem services that you are concerned about. So that's something to keep in mind, that the nitrogen deposition rates in India in general are high, and even in the Himalayas. There are other things which are not part of my work, but I would like to mention that since we're talking about global change, the biomass burning emissions from South Asia through the Himalayas, these are impacts that are happening. And so we are concerned about those types of drivers of hazards as well. Now, this is a piece of work where we compared using time series of remotely sensed data, NDVI 3G data, as well as CRU climate data, both on temperature and precipitation. We looked at pan-tropical systems, mountain systems, across all the different continents in Central and South America, East and Central Africa, South Asia, which is basically the Himalayas, and then Southeast Asia. And this is I'm just sharing the results for the Himalayas. So we did see, so you see the warming trend over the period of record. But what is interesting is the browning that we saw in terms of starting in the mid 90s. The many parts of the Himalayas had a browning tendency. Browning is basically loss of photosynthetically active foliar biomass. So either you have lower photosynthetic rates, they're becoming less green in some sense, or the leaves are being shed, there is less canopy cover, and so on. So that browning incident happened sometime in the mid 90s, and it continued up to 2005. So this is, and so we were curious to see what could be explaining that. And then this is just to show you the variability across the Himalayas. So you can see that the browning is consistent in many parts of the Himalayas, even though there's a lot of variability amongst the sites. And along with the browning, we also had an increase in the amplitude of the annual cycle, of phenological cycle. So you can see that the amplitude is increasing, the variability is also increasing over a period of time. So these are some of the changes that we observed using the remotely sensed data in our models, using Bayesian dynamic linear models. So this greening sense slope, you can see that a large number of pixels are on the negative side of it, which means that they were actually browning. And then a few greening pixels were seen at a much higher elevation. So a lot of browning happened during this time. In terms of we see that the response of NDVI to temperature, which is basically a time-varying regression coefficient, that time-varying regression coefficient plunged from the early 90s, and then it started recovering after 2000. But you can see that there is a big negative response of vegetation to temperature, and then the response to precipitation was much less pronounced. It's much more you can see that there are a lot of perturbations, a lot of interannual variability, a lot of complexity in the and if you just take the average, it might look as if it's hovering around zero, but actually there are a lot of years in which the response was positive, and then a large number of years in which the precipitation was not able to compensate for the impact of the warming effects from the atmosphere. So in some sense, precipitation is not able to compensate for the negative impacts of warming. So in some sense, it's a temperature-induced moisture stress that was affecting the systems. So whenever we see any result based on remotely sensed data and climate data, our first null hypothesis is that this is an artifact of the information of the maybe the data, or there's some other issue. So what we did is we went to some of the work that was done in Kumaon at that time. Luckily, we found sites where leaf water potential was measured. Now, 1999 was a very 1998-99 was the El Nino year, and the leaf water potentials in some of the oak forests in the Western Himalayas plunged. So actually what happened is typically you get about 160 mm of rainfall between September to May, which is like a post-monsoon period in the Western Himalayas. And in 1999, only 26.5 millimeters of rainfall fell. So it was a very severe stress on the vegetation. And this actual measurement was completely coinciding with the plunge that we see around 98-99 period. And then there's a recovery after that. So, so we were happy to find some corroboration from actual direct measurements of the response of vegetation on the ground. So this is just to mention the excellent work done by Zobel and his colleagues, and Dr. Singh and other colleagues in the Kumaon Himalayas, and where they mentioned that instead of getting 160 mm, which is the mean rainfall for that period, they ended up getting only 26.5 mm, and then the temperature was also very high, 31 degrees Celsius compared to 25 degrees Celsius in normal years. So it was a severe stress period, and so what they say is that they confirm the hypothesis that Himalayan trees suffer significant water stress, and of course there's a variability in how the different forest types respond to this water stress. And that's something that I'll be coming back to a little later in the talk. And so this greening and browning has been corroborated by other studies as well. These are other folks who followed after we published our work in Global Change Biology. There has also been other pieces of work that have talked about both greening and browning in different parts of the Himalayas. So I'm not going to get into the details of that. This is another work which is showing that. And here I just mentioned, I had developed many years ago for the Western Ghats. I developed a multi-date NDVI based monolobis distance approach, basically an eco-climatic distance, which is basically in some sense, the distance of any pixel in eco-climatic space to some reference pixels, in which case the reference pixels in this case happen to be stable evergreen forest in some part of South India. And so you can see the negative part here and the positive part here, and you can see that many parts of the Himalayas are impacted by negatively, and there are some greening aspects as well. So greening and browning is something that is happening in the Himalayas, and so it's not a very consistent response to climate change alone. Of course, there are other drivers. Land use and land cover change. It could be other types of nitrogen deposition, CO2 fertilization effect. We really don't know enough about but definitely temperature-induced moisture stress is one of them. But is the greening associated necessarily with healthy forest growth? We know that quite a bit of invasive species have actually come in, and they have proliferated in many parts of the Himalayas. So this is one of them, Lantana camara. So whenever we talk about greening in the Himalayas, we have to be aware that some of the space of the original native species is being taken over by these invasive shrubs. And of course, they have their own hydrologic impacts. They have their own responses to nutrients and their role in the carbon cycle. So this is something that we have to keep in mind. The other thing that's been happening, which has been noted by some very good scholars across India and Nepal, is the pine and oak systems. So there are some shifts that are being seen with broad-leaved oak for oak-dominated forests giving way to pine, both as a result of land use and land cover change, possibly also because of climate change. It's not very clear, and of course, pine consumes much more uh, water in terms of its through transpiration. So that's another factor to keep in mind, that when we see these shifts between from oak to pine, we are going to be also having impacts on the local hydrology as well. So, so overall, when we want to look at the relationship between forest cover and dry season stream flow, this has been an area of research for many decades, but it can be summarized in the form. Currently, we have these three hypotheses: that dry season stream flow, when you have a seasonal climate like we have in the Western Himalayas or in Western Ghats for that matter, where you have a dry season of 3 to 4 to 5 months. So the stream flow in the dry season is very important for sustaining ecosystems as well as for sustaining humans. So we are interested in the dry season stream flow. So the response of dry season stream flow to changes in forest cover can be one of three types. If you have infiltration and recharge to groundwater dominating over you can see this black arrow compared to the lighter gray arrow. So that means that infiltration and recharge is dominating over the evapotranspiration. Then you have the so-called sponge effect, which many of our forest-loving colleagues and friends would know. That is the usual paradigm that we use for making a case for conserving forests. So that's the sponge effect. You can actually have evapotranspiration and infiltration and recharge balancing each other out. So actually, there might not be a net effect of forest cover change on the dry season stream flow, and that's the neutral effect. And then you have the evapotranspiration dominated paradigm, where evapotranspiration dominates over the infiltration and recharge capacity of those forests. And a bulk of the studies until very recently, where 70% of the studies from instrumented catchment, very sanitized control experiments, which were very small in size, were dominated by the evapotranspiration paradigm. But now we are seeing from Costa Rica, where I've been working with colleagues, as well as in the Western Ghats, we are actually seeing evidence that supports the sponge effect as well as the neutral effect hypothesis. And so this is just a quick review of the work from the Western Ghats and Costa Rica, where we found a gain of 3.3 millimeters of dry season stream flow for every 1% increase in forest cover, both during the deforestation and recovery phase that we were able to work in. Does this happen in the Himalayas? So here is some recent work, which is by Nusrat Kazi and Brunzil and other colleagues, Dr. Rai and Gimire, where it shows that if you have a relatively intact broadleaf forest in the Himalayas, the subsurface flow regimes are maintained, and then the more surface flows are observed in the degraded catchment. So you can see that the top part of this is the intact forest, and this is the degraded forest. And so this is somewhat, it is supporting one of the hypotheses, three hypotheses about the sponge effect, definitely. But what we are now learning is that with increases in rainfall intensity under climate change, subsurface flow can also become rapid. So here are examples of soil pipes, big macropores, these are from the Western Ghats and other parts of Southeast Asia, but they possibly exist in some of the Himalayan systems as well, definitely in the Eastern Himalayas, and also in the very fractured and very active, because the Himalayas are a very young system, tectonically unstable, geologically young, and so a lot of fissures and cracks and subsurface flow mechanisms could be dominant. So what we found from our work from different sites, so we used instrumented catchment data from our sites in South India, in the Western Ghats, as well as from around the world, and we found that the residence time of water is a non-linear function of the rainfall intensity, that is millimeters per 15 minutes. So this is using high resolution instrumented catchment data. So this suggests that rainfall intensity, the role of a rainfall intensity in flood models had earlier been underestimated. And given this non-linear relationship between the residence time of water and rainfall intensity, this suggests that this is something that could become more prevalent even in forested catchments. So we could be having flooding emerging from headwater catchments, which might be forested, but the subsurface flow systems are getting activated by highly intense rains. So if we are going to see more intense rains in parts of the Himalayas, we should be testing this hypothesis with instrumented catchment data. So some evidence from this is that there is work which has been done suggests that transient groundwater storage with about a 45 days response time is an important part of the discharge of Himalayan rivers and streams. So this was recent work, 2012. And so I think this is something, this was of course done in central Himalayas and Nepal, but I think that we should be pursuing this in the Indian part of the Himalayas as well, is what is the role of the transient groundwater and whether it can actually contribute to rapid subsurface flow as we have seen in parts of the Western Ghats and other parts of the world. So now coming back to other aspects of how vegetation is involved. So vegetation can play a very important role in the recycling of moisture by land systems. Now this is a very active area of work in other parts of the world. So we know, for example, that 25 to 50% of the rainfall that falls within the interior of the Amazon forest, for example, is contributed by the recycling of evapotranspiration from the same forest. Now, the recycling of moisture and feedback to the monsoon was very poorly studied in India until very recently, and now there is emerging work, and parts of Northeast India are actually seen as a hotspot in terms of feedback to the monsoon. So in some sense, it's vegetation playing a role in influencing the monsoon dynamics. So this was a piece of work which was published in Nature in 2012 as Franklin, where basically any moisture, any air mass that was passing over well-vegetated surfaces had more than twice the amount of moisture than air which was not exposed to vegetation. And I've extracted the Indian part of that paper, that work, and you can see that Himalayas are definitely in terms of the evapotranspiration contribution, they rate pretty high along with parts of the Western Ghats. So the Western Ghats and the parts of the Himalayas are going to be very important in contributing to feedback to the monsoon. And you can see that the stippled portions are areas which are significant at the 95% confidence level. So India is well within the impact, even though we thought that our narrow strips of forest possibly cannot be playing the same role in influencing rainfall like they do in other parts of the world, like in the Congo Basin or Amazon or some other parts like in Southeast Asia. But evidence is mounting that this is something that merits investigation. The other piece of work that is really interesting is that came from work done in Nepal, where even when you have local systems in the Himalayas, which are cut off from the monsoonal flow for some days at a stretch. So you can actually have, depending on the aspect and location, you can actually have a site in the Western Himalayas or the Central Himalayas, or for that matter, the Eastern Himalayas, which is not influenced by the monsoon flow for some days, or sometimes it's isolated from it. And even then they found that the local rainfall, the diurnal cycle in the local rainfall was being sustained by recycling of the soil moisture through evapotranspiration. So 15 to 35% of the moisture from the local ecosystems is recycled back as rainfall. This was based on instrumented studies using a variety of techniques, and you can look up this paper. So what this suggests is that even so we always used to think that the monsoon flow is the main source of that monsoon dynamics. But locally, within some parts of the Himalayas, the well-vegetated surfaces, the forests, can make a significant contribution to maintaining the diurnal cycle. As you know, in the Eastern Himalayas, for example, in Sikkim, we get rain in the night. So, and of course, in the Western Himalayas, it's slightly different. So there is these mechanisms, the local mechanisms, which are being sustained by high evapotranspiration rates during the daytime, which then are fed back into the rainfall system. So why should we be interested in this? We can see that winter rainfall, remember that I was just talking earlier about what happens when winter rainfall is very poor in the Himalayas. We can have a negative effect on vegetation and so on. You can see that these are the trends in the winter rainfall from 1982 onwards. And you can see that the western and central Himalayas have a much more negative on the negative side of the trend compared to the eastern Himalayas. So the clear differences between the two systems in terms of the November to April rainfall. So, and remember that post-monsoon rainfall is an important driver of the productivity of broadleaf forests in the Himalayas. So another piece of work that I was lucky to be part of, Don Sebastian from IIT Bombay, I was on our PhD committee, so we published this piece of work in 2019, and she was able to show that the Western Himalayas are particularly sensitive to winter precipitation compared to other types of forests in India. So when you take the Central Indian forests, the Eastern Himalayas, Northeast, Western Ghats, and so on, the Western Himalayas have a very significant role of winter precipitation in terms of the response of vegetation. So again, to bring in, so here's the effect of radiation, and here is the pre-monsoon precipitation, monsoon precipitation, pre-monsoon precipitation, and winter precipitation. And winter precipitation is clearly very important for the Western Himalayas. And so any trends, negative trends that we see in winter precipitation in the Western Himalayas is likely to have a negative impact on in our forests. The other thing that is not captured in rain gauge data is that many other phenomena such as cloud stripping, that is the direct interaction of vegetation with clouds and direct transfer of moisture from clouds to the vegetation, that doesn't come into a rain gauge. Why? Because rain gauges are kept in open areas where there is far away from a canopy. Mist, fog, snow melt, these are all sources of moisture which are sustaining ecosystems, the epiphytes, many other types of aquatic ecosystems. They are disappearing according to local people, local knowledge, and of course we know about snow melt. But in terms of cloud stripping, mist, and fog, there are reports from people studying epiphytes and so on that the vegetation in the Himalayas could be impacted by the loss of these unique moisture regimes, which is happening because of warming. And as I said, you need special techniques to capture this because you can't get it from a rain gauge. So overall, so vegetation in the Himalayas is showing both greening and browning responses to climate change, and I must add other drivers of global change. Extreme rain events are major perturbations, both through direct and indirect impact on landslides. Now, remember, a landslide can have a big impact on vegetation, and so there are many eminent researchers in IIT Roorkee and elsewhere who are actually been studying all the geophysical aspects, and so they are much more capable of telling us about what's happening to landslides in terms of the Himalayas. I will just come to now back to the vegetation. Now, how can vegetation respond to moisture stress? So we already know from ground measurements as well as from remotely sensed measurements that for example, the vegetation in Western Himalayas is undergoing moisture stress, temperature-induced moisture stress during the dry season. Now, plants can respond in two ways. Now, if you are very conservative in terms of responding to moisture stress, you can shut off the stoma and you can signal to the roots to stop trying to absorb water because there isn't enough water in the. So basically, you have a negative soil water potential that gets signaled to the leaf. So you get a negative leaf water potential, and then there's a signaling system within the plant, and it can shut down the stoma. And so you won't have the risk of what is known as hydraulic failure, which is embolism. So if you have a break in the xylem column, you can actually kill the plant, or you can have severe damage to local tissues. So some species of trees and plants are very conservative. They will shut down photosynthesis at the first encounter with moisture stress. But if you keep doing that, what will happen? You will eventually die of carbon starvation. Because if you're not photosynthesizing by shutting off your stoma, you are going to run out of carbon to invest in new leaves, in flowers and buds and bark and every other thing that a plant needs to grow. So it's a challenge. Now, which species of Himalayan trees and shrubs are going to be taking their hydraulic and simplistic failure route, or they are going to be guarding against carbon starvation? Are they going to avoid hydraulic failure, or are they going to try to prevent carbon starvation? So this depends on the age group of the whether it's seedlings or whether it's adult tree. So very little information is available on how Himalayan trees are going to be, which strategy are they going to be choosing and responding to. So this is something that I am flagging as a knowledge gap. And we have seen from our instrumented work where we measured sap flux, which is Manish Kumar work in Sikkim, is that the transpiration rates of just two different species of broadleaf trees, they can be very different at the same site. So different trees are going to be responding in very different ways. And similar work needs to be done in the Western Himalayas, because in the Western Himalayas, you actually have a much more pronounced dry season. In the Eastern Himalayas, we actually get some more moisture even in the so-called dry season. And we also found that secondary forests, that is forests which are growing rapidly after an initial disturbance, they have much higher rates of transpiration compared to more older forests. So now there are other things which are happening. It's not just about climate change and nitrogen cycle and so on, but we are also having other types of dangers which are emerging in the Himalayas. We know that the Himalayas are tectonically unstable. The geology is extremely fragile. And we also know that extreme rain events are battering the Himalayas, Western Himalayas. We've heard about those massive cloud bursts and other things just a few years back. And yet, in terms of embarking on projects, we now have massive levels of tree cutting and widening of roads where large number of landslides are emerging because of cutting into entire hillsides. So this is going to happen over almost 1,000 kilometers of roads penetrating through the Char Dham project. Now, these are the type of things where scientists need to get involved and contribute to informing policy before it's too late. Because the damage that we are doing to the fragile Himalayas through such initiatives, in spite of all the evidence that we have from the Kedarnath disaster and other disasters in the last few years, it definitely needs for us to be involved in this. This is again, Manish, my student, took a picture of this landslide in the Western Himalayas just a few weeks back. And you can see that the landslides are ripping through entire vegetated slopes, both natural, so-called natural, but much more induced by possibly more extreme rain events and so on, but also now because of road building and tunneling and blasting and so on. So you can see the impacts of such extreme events from some years back. A lot of the debris from hydropower projects, from road building, the cutting of entire hillsides, the blasting of entire hillsides, all of that debris is falling into our rivers in the Himalayas. Again, posing a clear and present danger in terms of sediment buildup and also more potential for flooding and downstream disasters. So to conclude, there are a lot of complexities and uncertainties in terms of not just climate change, but other drivers of global change on Himalayan ecosystems. We definitely need to have long-term instrumented sites where we can keep track of what's happening and have a better understanding of the dynamics. And we need to emphasize non-climatic stresses. We have seen that if you need to have successful adaptation to future climate change, we need to have a better understanding of non-climatic stressors on vegetation and ecosystems so that they are better able to cope with changing climate and also in terms of adaptation of local communities and so on. We need to be looking at projects that are going to have big impacts on the local ecology, and ecosystems are going to be changing with new species composition and even with invasive species. So maybe we need to explore adaptation to changing ecosystems as well as an option, because if it's difficult to undo that type of change, maybe we need to explore how we can coexist with some of those newly evolving and novel ecosystems. So I'm going to end here, and I'm very thankful to the organizers of the Co-Prepare project for giving me this opportunity. It's a pleasure and privilege. I would like to acknowledge the Natural Environment Research Council of the UK, as well as the Department of Biotechnology and the Ministry of Earth Sciences for supporting my work in the past, and lots of my colleagues and friends have contributed to the current understanding that I have. And thank you.